Hello, today's topic of lecture is complex variable part 3, that is analytic function. I am S.R. Gaikwad, assistant professor in Department of Mathematics, Arts, Commerce Science College, Yawal. Please subscribe my YouTube channel Parishram Maths Academy. Now first, derivative. You can find the derivative of function of complex variable. Let f of z be a function of complex variable z. If the limit delta z tends to 0, f of z plus delta z minus f of z upon delta z is exist. If value of this limit is exist, then this limit is called derivative of function f of z with respect to z, and it is denoted by df by dz or f dash of z. And therefore f dash of z equal to limit delta z tends to 0 f of z plus delta z minus f of z upon delta z. The value of limit nothing but derivative of the function f of z with respect to z. Next, definition of analytic function. A function f of z of complex variable z is said to be analytic at a point z naught if f dash of z is exist at each point z in the some neighborhood of z naught. It means at each in the neighborhood of z naught the value of f dash of z is exist. It means function f of z is differentiable in the neighborhood of z naught. Then the function f of z is called as analytic at point z equal to z naught. And therefore a function f of z of complex variable z is said to be analytic in domain capital D if the function f of z is analytic at each point of D. If at every point of D function f of z is analytic, then f of z is analytic in domain capital D. Cauchy-Riemann equation, that is CR equations. Let u and v are real valued function of two variable x and y. Then the equations ux equal to vy and vx equal to minus uy are called Cauchy-Riemann equation. Here u and v are real valued functions having first order partial derivatives and satisfy the condition ux equal to vy and vx equal to minus y. These two equations are called as a Cauchy-Riemann equation. It is also called as a CR equations. Necessary condition of analytic function. One important theorem. The necessary condition that a function f of z equal to u in bracket x comma y plus I into v in bracket x comma y be analytic at point z equal to x plus iy is that at point x comma y the real and imaginary part u and v of function f of z satisfy CR equations. It means if f of z function is analytic, then we have to prove the real and imaginary part. It means u and v satisfy the Cauchy-Riemann equations. Proof. Let f of z equal to u in bracket x comma y plus I into v in bracket x comma y be analytic function. This given function f of z is analytic. Function is analytic, it means function f of z is differentiable, and function f of z is differentiable, it means f dash of z is exist. F dash of z is exist, and therefore f dash of z equal to limit delta z tends to 0 f of z plus delta z minus f of z upon delta z exist. It means value of limit is exist. And value of limit is exist, it means along different path value of limit is same. Now we can find the value of limit along two different path. First we take a path delta z tends to 0 along real axis. Along real axis value of delta y is 0, and therefore delta z equal to delta x plus I delta y, but value of delta y is 0 and therefore equal to delta x, and therefore delta z tends to 0 implies delta x tends to 0, and therefore f dash of z equal to limit delta x tends to 0 f of z nothing but x plus iy plus delta z nothing but delta x minus f of x plus iy upon delta x, and therefore equal to limit delta x tends to 0 f of x plus delta x plus iy minus f of x plus iy upon delta x. and therefore if limit delta x tends to 0, we can express function u in terms of u and v, and therefore u in bracket x plus delta x comma y plus I time v in bracket x plus delta x comma y minus value of f of x plus iy is u in bracket x comma y plus I time v in bracket x comma y upon delta x. Then we can simplify it, we get limit delta x tends to 0, u in bracket x plus delta x comma y minus u in bracket x comma y upon delta x plus, from this two term we can take I as common, into v in bracket x plus delta x comma y minus v in bracket x comma y upon delta x. Here term of x is variable, term of y is constant in both term upon delta x, and here limit delta x tends to 0, and therefore value of this limit nothing but derivative of function u with respect to x, and value of second nothing but derivative of function v with respect to x partially, that is ux plus I time vx, and therefore f dash of z equal to ux plus I into vx, which is equation 1. This value of f dash of z along real axis. Next, we can find the value of f of z. We take a path delta z tends to 0 along imaginary axis. It means along imaginary axis value of delta x is 0, and therefore delta z equal to delta x plus I delta y. Value of delta x is 0 and therefore equal to I delta y, and therefore delta z tends to 0 implies delta y tends to 0, and therefore f dash of z equal to limit delta y tends to 0 f of x plus delta x is value of z plus value of delta z is I delta y minus f of x plus iy upon delta z is I delta y equal to limit delta y tends to 0 f of x plus, we can take here I as common, I in bracket y plus delta y minus f of x plus iy upon I delta y, and therefore equal to limit delta y tends to 0. We can express function in terms of u and v. Therefore u in bracket x comma y plus delta y plus I time v in bracket x comma y plus delta y minus value of f of x plus iy is u in bracket x comma y plus I time v in bracket x comma y upon I delta y. Here upon I, first you can take 1 upon I, then into in bracket u in bracket x comma y plus delta y minus u in bracket x comma y upon delta y plus taking I common plus I into v in bracket x comma y plus delta y minus v in bracket x comma y upon delta y. Here term of x is constant, term of y is variable upon delta y, and limit delta y tends to 0, and therefore by definition of partial derivative, value of this limit nothing but derivative of u with respect to y, and value of this limit nothing but derivative of v with respect to y partially, that is uy plus I time vy. Now we know that 1 upon I is same as minus I, and therefore minus I into uy plus here minus I into I, that is minus I square, value of I square is minus 1, therefore minus minus plus here vy, and therefore f dash of z equal to minus I into uy plus vy, this value of f dash of z along imaginary axis. We know that value of f dash of z exists means along two different path value of limit is same, and therefore from equation 1 and 2 we get ux plus I vx equal to minus I uy plus vy by equating the value of f dash of z, and then by equating the real and imaginary parts we get ux equal to vy and vx equal to minus uy. It means u and v satisfy Cauchy-Riemann equation, and therefore f of z equal to u in bracket x comma y plus I time v in bracket x comma y be analytic function, then u and v satisfy Cauchy-Riemann equations, that is ux equal to vy and vx equal to minus uy. Example, if f of z and f of z bar are analytic functions of z, then show that f of z is constant function. Solution, let f of z equal to u plus iv be analytic function of z. Function f of z is analytic, it means u and v satisfy Cauchy-Riemann equation, it means ux equal to vy and vx equal to minus uy. Also f of z bar equal to u minus iv be analytic function of z. If f of z is analytic, at that time ux equal to vy and vx equal to minus cy. F of z bar is also analytic and therefore ux equal to minus vy and vx equal to uy. Then from this equation 1 and 2, in equation 1 ux equal to vy, in equation 2 ux equal to minus vy. By taking the addition ux plus ux, 2ux plus vy minus vy cancel, that equal to 0. It means ux equal to 0. Also, from this equation number 1, vx equal to minus uy. From equation 2, vx equal to uy. The vx equal to minus uy, vx equal to plus uy. Again, by taking the addition, 2vx equal to 0. It means vx equal to 0. And therefore, f dash of z equal to ux plus I time vx, but value of ux is 0, value of ux is also 0. It means f dash of z equal to 0. F dash of z equal to 0, it means the derivative of the function f of z is 0. It means f of z is a constant function. Next, second example. If f of z is analytic function with constant modulus, then show that f of z is constant function. Solution. Let f of z equal to u plus iv be analytic function with constant modulus. F of z is analytic and therefore u and v satisfy CR equation. Therefore ux equal to vy and vx equal to minus uy. F of z has constant modulus, it means mod of f of z equal to k, comma k is constant. And therefore, as f of z equal to u plus iv, mod of f of z nothing but root of u square plus v square equal to k, squaring, and therefore root u square plus v square equal to k square, equation 2. Then we can differentiate equation 2 with respect to x. Partially we get derivative of u square is twice u into ux, derivative of v square is twice v into vx, k is constant term, derivative of k is 0. Then by dividing 2, we get u into ux plus v into vx equal to 0. Again, differentiating equation 2 with respect to y, partially we get derivative of u square with respect to y is twice u into uy plus derivative of v square is twice v into vy, derivative of k square is 0. And then by dividing 2, we get u uy plus v vy equal to 0. Now, u and v satisfy CR equation. It means ux equal to vy and vx equal to minus uy, and therefore the here value of uy nothing but minus vx, and here vx nothing but vx from here vy equal to, here uy equal to minus vx, and here vy equal to ux. And then we can solve equation number 3 and 4, and therefore multiply equation 3 by v and equation 4 by u, and then by subtracting we get, if you multiply equation 3 by v, we get uv into ux plus v square into vx equal to 0. If you multiply equation 4 by u, we get minus u square into vx plus uv into ux equal to 0. If we take this subtraction, at that time these two terms cancel, this term minus minus plus, and therefore u square plus v square bracket complete into vx equal to 0. But value of u square plus v square is not equal to 0, and therefore value of vx equal to 0. Also, multiply equation 3 by u and equation 4 by v, and then adding we get sorry. If you multiply equation 3 by u, we get u square into ux plus uv into vx equal to 0. Multiply equation 4 by v, we get minus uv into vx plus v square into ux equal to 0. And then by taking their addition, if we take their addition, this plus minus these two terms cancel. From these two terms, we can take uxx common, and therefore u square plus v square bracket complete into ux equal to 0. But u square plus v square is not equal to 0, it means ux equal to 0. We get vx equal to 0, ux equal to 0, and therefore f dash of z equal to ux plus I time vx. But value of ux is 0, value of vx is 0, and therefore f dash of z equal to 0, derivative of f of z is 0, and therefore f of z is constant function. Next, Laplace differential equation. Let u in bracket x comma y be a function of two real variable x and y. Then the partial differential equation dou by square u of dou by x square plus dou by square u of dou by y square equal to 0. This partial differential equation is called a Laplace differential equation. Now, the operator dou by square of dou by x square plus dou by square of dou by y square is denoted by delta square, and therefore the Laplace differential equation is delta square of u equal to 0. Next, there is one more important theorem. The real and imaginary part of an analytic function satisfy Laplace differential equation. Proof. Let f of z equal to u plus iv is analytic function. Here u and v are nothing but u is real part and v is imaginary part of f of z. As f of z is analytic, therefore u and v satisfy CR equation. Therefore ux equal to vy and vx equal to minus uy. Now, from this equation here ux equal to vy, and from this second equation uy equal to minus vx, and therefore uxx equal to vyx and uyy equal to minus vxy. But vyx and vxy both are same, and therefore uxx plus uyy equal to uxx nothing but vyx minus uyy is vxy, but both are same, therefore their subtraction is 0. Therefore uxx plus uyy equal to 0, and therefore u satisfy Laplace differential equation. Also, from CR equation vy equal to ux and vx equal to minus uy. By differentiating, therefore vyy equal to uxy and vxx equal to minus uyx, but uxy and uyx both are same, and therefore vxx plus vyy equal to minus uyx plus uxy. These both terms are same, therefore their subtraction is 0. Therefore vxx plus vyy equal to 0, and therefore v satisfy Laplace differential equation. Therefore u and v satisfy Laplace differential equation. It means the real and imaginary parts of an analytic function satisfy Laplace differential equation. Okay. Next, harmonic function. Definition. A real function u in bracket x comma y of two real variable x and y, which has continuous partial derivatives of first and second order and which satisfy Laplace differential equation, is called harmonic function. It means the function u satisfy Laplace differential equation, and then such function u is called as a harmonic function. Now, the real and imaginary parts of the analytic function f of z equal to u plus iv. If function f of z is analytic, then real and imaginary parts satisfy Laplace differential equation, and therefore the real and imaginary part, that is u and v, are harmonic functions. And therefore f of z equal to u plus iv is analytic function, then u is called harmonic conjugate of v and v is called harmonic conjugate of u. Now, construction of analytic function. First, to construct analytic function whose real part is given, let f of z equal to u plus iv be analytic function and u is given. Now, f of z function is analytic, and therefore u and v satisfy CR equations, and therefore ux equal to vy and vx equal to minus ui. Now here u is given, we can find the function f of z equal to u plus iv, therefore we must find v, and therefore first we find v. We have dv equal to, by definition of total derivative, dv equal to dou by v by dou by x into dx plus dou by v of dou by y into dy. It means vx dx plus vy dy. But by using CR equation, vx equal to minus uy and uy equal to ux, and therefore minus uy dx plus ux dy equal to, we can take m dx plus n dy. We find derivative of capital M with respect to y and derivative of n with respect to x, and by taking their subtraction is always 0. It means the differential equation dv equal to m dx plus n dy equal to 0 is exact differential equation. Now the differential equation is exact and therefore solution is given by v equal to integration of m dx by keeping y constant plus integration of terms in capital N which are free from x integration with respect to y plus constancy. The value of this integration nothing but we get value of function v, and therefore by putting the value of u and v we get analytic function f of z equal to u plus iv, and therefore when u is given, first we can find the value of v, then putting the value of u and v we get the function f of z equal to u plus iv. Second type, to construct analytic function whose imaginary part is given. Let f of z equal to u plus iv is analytic function and v is given. As f of z is analytic and therefore u and v satisfy CR equation, therefore ux equal to vy, vx equal to minus ey. To find u first, and therefore du equal to dA by u by dA by x into dx plus dA by u of dA by y into dy plus it means ux dx plus uy dy. But using CR equation, ux is same as vy and uy is same as minus cvx. Equal to we can take m dx plus n dy. Again, if we take derivative of capital M with respect to y, derivative of n with respect to x, then here u and v satisfy Laplace differential equation. Therefore, from this we get this, though both partial derivatives are same, and therefore differential equation m dx plus n dy equal to 0 is exact differential equation. As the differential equation is exact and therefore solution is given by u equal to integration of m dx by keeping y constant plus integration of terms in capital N which are free from x integration with respect to y plus constancy. The value of this integration nothing but we get value of u, and then putting the value of u and v we get analytic function f of z equal to u plus iv. And therefore either u is given or v is given, you can find the function f of z. Example, find the analytic function whose real part is x cube minus 3xy square. Solution, let f of z equal to u plus iv be analytic function and u equal to x cube minus 3xy square is given, that is real part is given. Now u is given and therefore ux equal to derivative of x cube is 3x square, derivative of 3xy square with respect to x is 3y square, and derivative of u with respect to y, derivative of first term is 0, derivative of y square is twice y and therefore minus 6xy. Then f of z equal to u, f of z is analytic function, it means u and v satisfy CR equation, it means ux equal to vy, vx equal to minus ey. First we can find u, and therefore we have dv equal to dA by v by dA by x into dx plus dA by v by dA by y into dy, and therefore dv equal to vx dx plus vy dy. But by using CR equation, vx equal to minus uy and vy equal to ux, putting the value of uy and vx. If you find derivative of this term with respect to y, nothing but 6x. Derivative of this term with respect to x is also 6x. Both are same. It means this equation is exact differential equation. And therefore, solution is v equal to integration of m dx by keeping y constant plus integration of terms in capital N which are free from x dy plus constancy. Therefore, v equal to integration of 6xy dx plus term free from x in n nothing but minus only minus 3y square. Then by integrating, integration of first term with respect to x, integration of x is x square upon 2, 2 cancel and therefore 3x square into y minus integration of y square is y raised to 3 upon 3, 3 cancel, that is y raised to 3 plus constancy. We get the value of v, and therefore putting the value of u and v we get the analytic function f of z equal to u plus iv. Value of u is x cube minus 3xy square plus I into value of v nothing but 3x square y minus y cube plus constancy. Simplify it, we get x cube plus 3rx square y minus 3xy square minus I into y cube plus I into c. Now this x cube plus 3I x square y minus 3xy square minus I into y. This first four terms are nothing but x plus iy bracket cube. This x plus y bracket cube expansion. But value of x plus iy is z, and therefore f of z equal to z cube plus I into c, which is analytic function f of z equal when real part is given. Okay. Second example. Find analytic function whose imaginary part is 3x square y minus y cube plus twice y. Solution. Let f of z equal u plus iv be analytic function, and imaginary part v equal to 3x square y minus y cube plus twice y is given. And therefore, from this we get vx equal to derivative of first term with respect to x, derivative of x square is twice x, and therefore 6xy, derivative of second and third term is 0. And derivative of v with respect to y, derivative of first term, derivative of y is 1 here, therefore 3x square minus derivative of y cube is minus 3y square plus derivative of twice y is 2. These are derivative of v with respect to x and with respect to y. Now, f of z is analytic. Therefore, u and v satisfy CR equations. Therefore, ux equal to vy and vx equal to minus uy. And therefore, first we can find the real part u. Therefore, by definition of total derivative, du equal to dA by u by dA by x into dx plus dA by u of dA by y into dy. That is ux dx plus uy dy. But by using CR equations, value of ux equal to vy and vx, uy equal to minus vx. Putting the value of vy and vx, value of vy is 3x square minus 3y square plus 2 dx minus value of vx nothing but 6xy. Derivative of this term with respect to y nothing but minus 6y. Derivative of this term with respect to x nothing but minus 6y. Both derivatives are same, and therefore the differential equation is exact differential equation. And therefore the solution is given by u equal to integration of m dx by keeping y constant plus integration of terms in n free from x dy plus constancy. We can take this value of capital M. There is no term in capital N free from x, and therefore we can take here 0 dy. Integration of first term with respect to x. First integration of x square, x raised to 3 upon 3, 3 cancel, and therefore x raised to 3 minus 3y square. 3y square is constant term. Integration of this term with respect to x is minus 3xy square plus integration of 2 is 2x plus constancy. We get the value of real part u. Then by putting the value of u and v, we get the analytic function f of z equal to u plus iv. Now from the value of u nothing but x cube minus 3xy square plus twice x plus c plus I into value of v is given 3x square y minus y cube plus twice y. Simplify. First x cube minus 3ix square y minus 3xy square minus I into y cube, then plus twice x plus 2iy, and then plus constancy. That first you can take the terms of degree 3, and then terms of degree 2, and then constant term. The first four terms are nothing but x plus iy bracket. From this next two terms you can take 2 as common in bracket, x plus iy plus constancy. But x plus iy nothing but z, and therefore z cube plus twice z plus c, which is analytic function f of z when imaginary part is given. Next, show that the function u equal to e raised to x into cos of y is harmonic function. Determine harmonic conjugate and analytic function f of z. Solution. Given that u equal to e raised to x into cos of y, first we have to prove function u is harmonic function. That is, we have to prove function u satisfy the Laplace differential equation. For this, first we can find ux, derivative of u with respect to x nothing but e raised to x into cos y. Again differentiating ux equal to e raised to x into cos y. Derivative of u with respect to y is derivative of cos of y is minus sin of y, therefore minus e raised to x into sin y. Again by differentiating derivative of sin y is cos y, that is minus e raised to x into cos y. And then by taking the addition, therefore uxx plus uyy equal to e raised to x cos y minus e raised to x cos y, subtraction is 0, and therefore uxx plus uyy equal to 0. It means u satisfy Laplace differential equation, therefore u is harmonic function. To find harmonic conjugate, let v is harmonic conjugate of u, and therefore f of z equal to u plus iv is analytic function. Now f of z equal to u plus iv is analytic function, therefore u and v satisfy CR equations. It means ux equal to vy, vx equal to minus cy. Now to find harmonic conjugate, that is we can find v, and therefore dv equal to dA by v by dA by x into dx plus dA by v by dA by y into dy. It means vx dx plus vy dy. But by using CR equation, vx equal to minus uy and vy equal to ux, putting the value of uy and vx. Value of uy is minus plus e raised to x into sin y dx, plus value of ux is e raised to x into cos of y. If you find derivative of coefficient of x with respect to y and coefficient of y with respect to both partial derivatives are same, it means this equation is exact differential equation. And therefore this solution is given by v equal to integration of m dx by keeping y constant plus integration of terms in capital N free from x dy plus constancy. Therefore integration of e raised to x into sin y dx by keeping y constant, plus there is no term in coefficient of dy free from x, and therefore we can take here 0 dy. Integration of first term with respect to x by keeping y constant, but sin y constant term here, integration of e raised to x is e raised to x, and therefore e raised to x into sin y plus constancy, which is value of v, and therefore we get the harmonic conjugate of u, which is harmonic conjugate of u. Now to find analytic function f of z, and therefore f of z equal to u plus iv. Value of u nothing but e raised to x cos y plus I into value of u nothing but e raised to x into sin y plus c. Simplify. From the first we can take e raised to x as common. Therefore e raised to x in bracket cos of y plus I times sin of y plus I into c. But cos of y plus I times sin of y is same as e raised to iy, and therefore e raised to x plus iy plus I into c, but x plus iy is z, and therefore f of z equal to e raised to z plus I into c, which is analytic function f of z. Okay, we can summarize this topic. First, definition of analytic function. First, must we remember the analytic function. The function f of z of complex variable z is said to be analytic at point z naught if f dash of z exists. It means f of z, derivative of function f of z is exist at each point in the some neighborhood of z naught. If the function f of z is differentiable in the some neighborhood of z naught, then function f of z is analytic at point z naught. The definition of analytic function. Next, Cauchy-Riemann equations. U and v are real valued function of two variable x and y. Then the equation ux equal to vy and vx equal to minus uy are called Cauchy-Riemann equations. If the function f of z is analytic, then u and v, that is real and imaginary parts, satisfy Laplace differential equation, that is ux equal to vy and vx equal to minus uy. Laplace differential equation, that u equal to u in bracket x comma y be a function of two real variable x and y. Then the partial differential equation dA by square u of dA by x square plus dA by square of dA by y square is called Laplace differential equation. If you satisfy this partial differential equation, then you must satisfy the Laplace differential equation. Harmonic function. A real function u in bracket x comma y of two real variable x and y, which has continuous partial derivatives of first and second order and which satisfy Laplace differential equation, is called harmonic function. It means function u satisfy Laplace differential equation, that dA by square u of dA by x square plus dA by square u of dA by y square equal to 0, then u is called as a harmonic function. These are important topics of this lecture. Thank you. Please like and share this video and subscribe my YouTube channel Parishram Maths Academy.